In 1912, the world's most powerful eruption began. An ash column rose 30 kilometers into the sky, and darkness covered half the world.
The 6th of June, 1912, Alaska. In 60 hours, 15 cubic kilometers of magma punch into the sky. The ash column rises 30 kilometers, 3 times the height of Everest. Darkness covers half the Northern Hemisphere, the most powerful eruption of the 20th century. Its name today, one person in 1,000 can tell you. This was not a mountain. This was not a peak. This was a hole. A hole in the ground that ripped open on a remote peninsula in southwest Alaska with no warning, no previous eruption, no earthquake swarms anyone bothered to record. The vent had no name. It had no monitoring station. It had no witnesses for the first 6 hours. And by the time the first witness looked up, the sky was already gone. The ash plume punched through the troposphere in under an hour. It reached the stratosphere by lunchtime. By the next morning, fine ash was falling on Vancouver. By the third day, on Wisconsin.
By the end of the month, particles were detected over Algeria. Average temperatures across the Northern Hemisphere dropped by close to a degree for the next 2 years. Crop failures followed across Europe and Canada. Sunsets across the Atlantic turned blood red. No one connected the events to a vent in Alaska. Krakatoa, 1883. 12 cubic kilometers of debris. 40,000 dead. The world remembers it. Tambora, 1815. Even larger. It triggered the year without a summer. The world remembers it. Vesuvius, 79 of the Common Era. Pompeii frozen mid-step. The world remembers it. Now, Alaska, 1912. Larger than Krakatoa. More than 5 times the ash of Vesuvius. And the world remembers nothing. For 41 years, every textbook gave the same answer. The volcano that erupted in 1912 was Mount Katmai. Every textbook was wrong. Katmai never erupted. The real source sat 10 kilometers away, and on that morning, it did not yet have a name. How can the largest eruption in modern history be forgotten? How can science name the wrong mountain for 4 decades and never correct the record in the textbooks the public reads? Who decides which catastrophes enter our collective memory and which slip away into footnotes? If a planet-shaking event can vanish within a single human lifetime, what else have we forgotten? And what is building right now beneath that same Alaskan peninsula with no instruments listening? By the end of this film, 3 things will be clear. Why the first witnesses on Kodiak Island spent 2.5 days in total darkness, convinced the world was ending. Why a botanist from Ohio walked into a valley of 10,000 smokes in the summer of 1915 and found something that should not exist.
And why a single geologist in 1953 quietly destroyed everything textbooks had taught 2 generations about what happened in June of 1912. The volcano has a name. It has been written into one of the smallest entries in the catalog of the United States Geological Survey. For most of the world, that entry might as well not exist. By the end of this film, that will change. Kodiak Island, the 6th of June, 1912, late afternoon. The sky to the west turns the color of wet iron. A fisherman named Ivan Orloff is sitting in a small wooden shack near Kaflia Bay on the Alaska Peninsula coast, less than 50 kilometers from the vent. He cannot know what is happening. There is no radio. There are no instruments. There is only the sound, a low, continuous thunder that he later describes as worse than any storm he has heard in his life. By evening, ash begins to fall like wet snow. Within hours, he can no longer see his own hand in front of his face. Orloff writes a letter. He does not know if he will live to send it. The letter survives. In it, he tells his wife Anyuta that the world appears to be ending, that a mountain is shooting smoke and fire, that the noise is constant, that he is dying. The letter would be published more than a year later. it remains one of the only contemporary written accounts from inside the ash zone. 160 kilometers to the east, on Kodiak Island, the situation is different and worse. Kodiak has a population of several hundred. It has a Russian Orthodox church. It has the United States revenue cutter Manning at anchor in its harbor, commanded by Captain Perry. On the 7th of June, the sky over Kodiak begins to darken at midday. By 3 in the afternoon, the sun is gone. By 6, every lamp in the town is lit. By midnight, ash is falling at a rate of 1 centimeter per hour. Roofs begin to groan. A few collapse outright. Breathing requires a wet cloth pressed against the face. Boots fill with ash within 100 meters of any door. For 2.5 days, Kodiak experiences total darkness. Not gloom, darkness. A lantern at arm's length is invisible. The temperature drops by more than 5 degrees in a region where June is supposed to be warm. The harbor surface freezes, not from cold, but from the sheer weight of ash piling on the water until it no longer behaves like water at all. Captain Perry takes the residents aboard the Manning. He orders the hatches sealed. He stations crew with shovels on the upper decks to keep the vessel from going under. The cutter survives. By the time the ash stops falling, 1/2 meter of gray dust covers the island. Buildings have collapsed. Wildlife is dead in the streets. The town will not fully clear the ash for another 2 years. No one on Kodiak sees the eruption. No one survives within 50 kilometers of the vent. The closest direct observers, fishermen, hunters, native Alutiiq villagers, flee or die.
The villages of Katmai, Savanoski, and Douglas are abandoned within hours. They will never be repopulated. 3 settlements erased in a weekend. And here is the detail the early reports missed entirely. When the United States Geological Survey sends its first investigators to the region 3 years later, they will find something none of the witnesses described, something the ash had hidden. A second story underneath the surface one, a story that will take 40 more years to read. The witnesses on Kodiak could be forgiven their confusion. They were trapped under 1/2 meter of falling ash. They could not see. They could not breathe. They could not measure. The scientists who arrived in the daylight 3 summers later, they cannot be forgiven so easily. The first scientific expedition to reach the eruption zone arrives in the summer of 1915, 3 years after the event.
It is led by a botanist from Ohio State University named Robert Fisk Griggs, working under the National Geographic Society. Griggs has no formal training in volcanology. He has been sent to study how plants recover after a catastrophe. He will return to the region 4 times across the next 4 summers. Each visit will overturn the conclusions of the visit before. In 1916, Griggs reaches the summit of a mountain called Katmai. This mountain has been declared the source of the 1912 eruption, partly because of its size, partly because of its location, partly because there is no other obvious candidate. Katmai stands roughly 2,400 meters tall, or rather, it did, before 1912. What Griggs finds at the summit is not a mountain, it is a hole. The peak of Katmai is gone. In its place, a caldera 3 kilometers wide, 4 kilometers long, and almost a kilometer deep. The walls are sheer. At the bottom, a lake has begun to form.
Its color is gray-green and unnaturally still. The wind across the rim is constant, dry, and warm, even in October. The air smells faintly of sulfur. Steam rises from cracks in the caldera wall. Griggs assumes he has found the answer. Katmai's summit collapsed. The missing rock, more than 360 meters of elevation, must have been ejected as the ash that buried Kodiak. The case appears closed. But a detail will not let Griggs sleep. The volume of material removed from Katmai's summit, measured carefully, comes to roughly 1 cubic kilometer. The volume of ash that fell on Kodiak, on the Alaska Peninsula, and on the surrounding ocean, measured by sediment cores, ash layers, and dust deposits across 3 continents, comes to 15 cubic kilometers. The numbers do not match. they are not close. They are off by a factor of 15. In 1919, Griggs publishes a paper raising the question: where did the other 14 cubic kilometers of magma come from?
The paper is read, the question is noted, and then it is set aside. For the next 34 years, official scientific literature continues to describe Mount Katmai as the source of the 1912 eruption. The discrepancy in volume is treated as a measurement error. There is, however, another mountain. Or rather, there is not. 10 kilometers west of Katmai's caldera, on the floor of a wide valley, sits a small lava dome. It is barely 400 meters across. It is barely 60 meters tall. It has the appearance of a pimple on the landscape, not a volcano. It is so small that early expedition maps fail to mark it as a feature at all. Griggs himself walks past it on his second visit. He notes it as an inactive vent. He moves on. In 1919, no instrument in the world can prove that this small gray dome, and not the Great Collapsed Katmai, is the actual mouth of the largest eruption of the modern era. The technology does not yet exist.
The geochemistry does not yet exist. The question, for now, has no way to be answered. It will wait for 34 more years. In 1916, on his second expedition, Griggs crests a ridge to the west of Katmai. What he sees below stops him. A valley, more than 20 kilometers long and several kilometers wide, is filled with a smooth, level, gray deposit. The deposit is hundreds of meters thick, and rising from its surface, vents, steam jets, thousands of them, tens of thousands of them, stretching from one end of the valley to the other. The air shimmers from heat. The ground is hot to the touch through the sole of a boot. Griggs names it the Valley of 10,000 Smokes. The name will stick. It is in fact an undercount. Later surveys estimate the number of active fumaroles at the time of discovery to be closer to 100,000. The valley floor is hot enough in places to scorch a leather glove on contact. Water poured from a flask boils on the rock.
Some vents register temperatures of 645 degrees centigrade, hot enough to melt lead, hot enough to forge iron without a forge. What Griggs is walking on is not lava. It is not ash. It is something called pyroclastic flow, a superheated cloud of gas, ash, and pumice that traveled at hundreds of kilometers per hour down the valley during the first hours of the eruption. The flow buried the original landscape under deposits up to 200 meters deep. In total, it covered more than 120 square kilometers, an area larger than the city of Paris. Everything beneath it was sterilized, the flora, the fauna, the soil, gone, replaced by a flat, lifeless plain that, 4 years later, was still cooling. The pyroclastic flow does not appear in the early eruption reports because no one saw it. It happened in the first 3 hours. It killed nothing directly because nothing lived in the valley. It moved like a shadow under the falling ash. By the time daylight returned to Kodiak, the flow had already cooled into solid stone, and no one outside the valley knew it existed. Griggs and his team photographed the valley exhaustively. Several thousand glass plate negatives are produced across 4 expedition seasons. They show steam columns hundreds of meters tall. They show men standing on a plain that resembles the surface of another planet. They show a landscape that, in 1917, looked unlike anything else on Earth. The plates are returned to Washington. They are cataloged by the National Geographic Society. Most have never been published. If the theme of geological catastrophes and forgotten epics interest you, subscribe to the channel. There are many more stories ahead that are not in the textbooks. And now, back to the heart of it. The Valley of 10,000 Smokes existed only because of one fact. The pyroclastic flow had to come from somewhere.
Magma at that volume, at that temperature, traveling at that speed, had to have a source. And the source could not be the collapsed summit of Katmai. The geometry was wrong. The angle of deposition was wrong. The direction of flow was wrong. The source had to be west. The source had to lie inside the valley itself. But in 1917, Griggs cannot prove this. He suspects it. He writes about it cautiously. He moves on. The valley is named. The catastrophe is documented. The wrong mountain remains in the textbooks for another 36 years. 1953. A young geologist named Garniss Curtis arrives in the Valley of 10,000 Smokes. He is working out of the University of California, Berkeley. The fumaroles by this time have mostly died. The valley is cooler, quieter. The fieldwork is no longer dangerous. It has become, for the first time, properly possible. Curtis is not looking for a controversy. He is looking for samples.
He spends the summer collecting pumice, ash, and lava from across the deposit zone. The pumice is so light that a fist-sized chunk floats on water. It is sharp enough on its broken edges to draw blood from a bare hand. He maps the distribution of materials. He notes the thicknesses. He records the chemistry. And when he returns to the laboratory in the autumn, he begins to find things that should not be there. The pumice from the eruption zone is not one type of rock. It is three. Curtis identifies rhyolite, the most explosive, gas-rich form, light in color and almost foam-like. He identifies dacite, intermediate, slightly darker, slightly denser. He identifies andesite, the densest, the least explosive, the most common in subduction zones. All three appear in deposits laid down within the same 60-hour window. All three came out of the same vent, at the same time. This should not be possible. A single volcanic chamber, by every existing model in 1953, produces a single dominant magma type. The presence of three distinct chemistries in one eruption suggests that the magma did not come from one place. It came from two, possibly more. Curtis then maps the deposits geometrically. He measures the thickness of pumice as a function of distance from each candidate vent. He overlays the patterns. The math gives a single, unambiguous answer. The center of the eruption, the actual mouth, is not Mount Katmai. The center is 10 kilometers west. The center is the small gray dome that Griggs walked past in 1916 and recorded as inactive. The dome has a name. It was given one by Griggs himself, briefly, in passing. Novarupta, Latin for newly erupted. The name had been forgotten by everyone except the United States Geological Survey, which kept it on file in an obscure entry. Curtis brings it back. In 1954, Curtis publishes his findings.
The conclusion is precise. Mount Katmai did not erupt in 1912. The eruption came from Novarupta. Katmai summit did collapse, but not because it exploded. It collapsed because the magma beneath it was drained. The chamber under Katmai was emptied through a lateral underground conduit, roughly 10 kilometers long, into the new vent at Novarupta. The roof of the empty chamber gave way. The summit followed it down. This process now has a formal name. Geologists call it magma piracy. One volcano steals the contents of another's chamber, and the original mountain collapses without ever erupting at all. It is rare. It is documented globally in only a handful of cases. Novarupta is the largest known example in human history. For 41 years, the wrong mountain had been named because it looked like it had exploded. In reality, Katmai had been gutted from below.
The actual source? A quiet 400-meter dome in a valley most maps did not bother to draw, had been mistaken for a remnant, a pimple, a footnote. Curtis is 41 years late, but he is right. In 1912, the world was already distracted. The Titanic had gone down in April. The Mexican Revolution was in its second year. The Balkans were quietly assembling the conditions of a global war. A volcano in a remote corner of southwestern Alaska with no deaths reported, in a place most Americans could not have located on a map, competed for attention with everything happening everywhere else. The first headlines about ash falling on Kodiak appeared in late June. By July, the Russian Orthodox Church in San Francisco had organized relief for displaced Alutiiq villagers. By August, the story had moved to the inner pages of the newspapers. By September, it had moved out of them entirely.
The next great news cycle, the sinking of European peace into industrial war, would arrive in the summer of 1914. The eruption began in June 1912. 2 years later, the world went to war. The catastrophe vanished from the news and from memory in the same season. Krakatoa, by contrast, killed 40,000 people in 1883. Tambora in 1815 killed over 100,000 directly and triggered a global famine. Vesuvius in 79 of the Common Era sealed an entire Roman city in volcanic stone. Each of these eruptions had what Novarupta did not. Each had a death toll. Each had an audience. Each had survivors who carried the story forward into the cultural record. Novarupta had none of that. The villages within 50 kilometers of the vent were evacuated in time. The displaced populations were absorbed into other settlements along the coast. The deaths from secondary causes, disease, exposure, hunger, were never tabulated as eruption casualties. The official death count, as recorded in most encyclopedias, remains 0. A catastrophe with no body count, the modern memory machine refuses to process. And yet, the consequences were planetary. Wes Hildreth, the United States Geological Survey volcanologist, who has spent most of his professional life studying Novarupta, has documented the global signature. Northern Hemisphere average temperatures dropped by close to a degree through the summer of 1913. Sunsets across Europe and North America turned an abnormal red, recorded in newspaper accounts, in oil paintings, in photographic plates, without anyone at the time linking the cause to Alaska. Fine ash particles were detected in Algeria. The acoustic shock waves from the eruption were recorded on barographs in Washington state, more than 2,000 kilometers from the source.
The eruption ejected an estimated 13 to 15 cubic kilometers of magma, more than the next 4 largest eruptions of the 20th century combined. By volume index, it ranks at 6 on the volcanic explosivity scale. The next event of comparable magnitude, Mount Pinatubo in the Philippines in 1991, produced roughly 1/3 the material and killed more than 800 people. The world remembers Pinatubo. The world does not remember Novarupta. What this comparison reveals is uncomfortable. Memory of catastrophe scales not with the size of the event, but with the size of the audience. A larger eruption with no witnesses, no deaths, and no broadcast infrastructure dies in the archive. A smaller eruption with cameras present enters the canon. The implication runs in both directions. There may be other Novaruptas in the geological record, events of comparable or greater scale hidden because no human civilization existed to record them. And there may be the next one, building now, beneath the same Alaska peninsula, with the same indifferent ocean above it. The instruments are better now, the audience may not be. The Alaska Peninsula is, geologically, one of the most active places on the planet. It hosts more than 50 active volcanoes. It produces, on average, 1 significant eruption every 2 years. Most of these eruptions are small. None has approached the magnitude of 1912. None. Yet. The modern monitoring network around Novarupta is more sophisticated than anything that existed 100 years ago. The Alaska Volcano Observatory maintains seismometers, gas sensors, ground deformation arrays, and satellite-based thermal imaging across the entire peninsula. The magma chamber beneath Katmai, the one that was drained through 10 kilometers of conduit in 1912, is partially refilling. The rate is slow. The seismic activity is quiet. There is no immediate warning sign that another event is imminent. There is also no guarantee that warning signs would be recognized in time. Novarupta itself produced almost no precursor activity. The first significant earthquakes were recorded in early June 1912. The eruption began 5 days later. In modern terms, assuming current monitoring, that interval would allow for a regional alert. It would not allow for full evacuation. The pyroclastic flow that buried the valley in 3 hours can outrun anything on the ground. The valley itself is now part of Katmai National Park, declared a national monument by President Wilson in 1918 on the strength of Griggs's expeditions. Wes Hildreth and his colleagues at the United States Geological Survey continue the long, slow work of mapping the deposits, refining the chronology, and tracking the gradual subsidence of the system. The fumaroles, once 100,000 strong, are now reduced to a few isolated vents near the dome itself. The valley is cooling. The smokes are fading. In another generation, the name itself may need to be revised. Standing on the rim of the Katmai Caldera on a clear Alaska night, the silence is total. The crater lake is black and motionless. The wind moves slowly across the rim. The dome of Novarupta is barely visible to the west, a small gray lump in a vast empty plain. There is nothing about the scene that suggests what happened beneath it in 1912. There is nothing about it that suggests what may yet happen beneath it again. This is, in some way, the deeper lesson of the eruption that no one remembers. Geological time is indifferent to whether anyone is watching. A catastrophe of planetary scale can occur, can shift the climate of an entire hemisphere, can erase 3 settlements and reshape a coastline, and can do all of it in a region empty enough that the official record reads, "No fatalities." The event becomes a footnote. The footnote becomes a citation. The citation becomes a forgotten paragraph in a textbook nobody opens. And then the cycle repeats. If the theme of geological catastrophes and forgotten epics interests you, subscribe to the channel and turn on notifications. There are many more stories ahead that are not in the textbooks. The question Novarupta leaves is not whether it will happen again. On geological timescales, eruptions of this magnitude occur on the order of once per century, somewhere on Earth. The last one, by every measure, was Pinatubo. The one before, Novarupta. The question is not whether, but where and when, and whether the next one will happen, like Pinatubo, in front of cameras and instruments and witnesses, or whether, like Novarupta, it will happen in a place empty enough to be forgotten within a single human lifetime. And if it does, will anyone be left to count what was lost?
Welcome to another Mystery Minute. Can you solve this magic? Like and subscribe for more.